This chapter now finishes on what we call the use of the heat of formation, along with all the other heats we've talked about since the start of the chapter, coming together under Hess's Law. Okay, so this final part is going to be, I suppose, the most important part of the chapter that we have looked at in terms of the examination, because this is where the maths happens. Okay, now I'm going to just preempt this particular class by saying that you have to know the definition for the heat of reaction, you have to know the definition for the heat of combustion, you have to know the definition for the heat of neutralization, and you will have to know the definition for the heat of formation, which is about to be given here. And you'll notice underneath we've got two words: elemental combinations. Okay, at the end of the day, no matter how anything is formed, the one thing we can say is that everything is formed from elements. So water, H2O, is formed from the elements hydrogen and oxygen. Okay, methane, CH4, formed from the elements of carbon and hydrogen. So everything, no matter what compound you have, that compound can be said to be made from its elements. And that's part, even half of the definition of the heat of formation. So what is the definition? Again, notice the following words. It is the heat change that takes place when 1 mole. Now I told you already, heat of reaction, heat of combustion, heat of neutralization, heat of formation. There are 4 definitions, 3 of which start with the same words. It is the heat change that takes place when 1 mole. And then you finish it according to what you're being asked. So in this case here, it is the heat change that takes place when 1 mole of a substance is formed from its elements, or 1 mole of a compound is formed from its elements. That is the definition for the heat of formation, and that is going to be crucial for moving forward into the mathematical aspect of thermochemistry. Okay, so there's your 4th and final definition. It is the heat change that takes place when 1 mole of a substance or 1 mole of a compound is formed from its elements. Now again, I'm going to ask you a couple of questions in terms of, do these reactions fit the definition? Does that fit the definition? So take a look at that. 2 moles of H2 plus 1 mole of oxygen gives 2 moles of water, and the heat change for the reaction is minus 561.6 kilojoules per mole. Now, think very carefully. Is that the heat of formation? What does the definition say? It's the heat change that takes place when 1 mole is formed. So go down to the side where you have your products. What do you notice? There are 2 moles. This is not an equation that represents the heat of formation. The heat of formation, therefore, would be all of this divided by 2. So it would be H2 plus a half O2 will give H2O, and delta H would be half that. So if I take 571.6 and divide it by 2, I'll get 285.8. Okay, and that would be the correct way to line up the chemical equation with the definition for the heat of formation. So please remember, it is the heat change that takes place when 1 mole of a compound is formed from its elements. Okay, and that's what we have to remember. So since the equation leads to 2 moles of H2O, then this is not an equation that represents the heat of formation. Okay, it is not representative. So you have to be very, very careful, because they're going to throw these at you with various different changes to make sure you understand your definitions. When writing equations for the formation of a substance, we need to remember 2 things. First of all, you're only allowed to form 1 mole. Okay, and secondly, you form that 1 mole of the compound from the elements in the compound. Now that's the key thing behind this particular equation. In writing the equation for the heat of formation of ammonia, we have 2 options. Here they are. Okay, now first of all, the first one is 1 mole of nitrogen gas plus 3 moles of hydrogen gas give 2 moles of ammonia. And in natural processes, that is what would happen. Because don't forget what Lussac said. Lussac said that everything, and even Dalton said the same thing, that elements and compounds, chemical reactions occur according to simple whole number ratios. Okay, so that's a foundation in chemistry. All reactions proceed according to simple whole number ratios. So what's this? This is 1 is to 3 is to 2. So from the point of view of chemistry, that's good chemistry. But from the point of view of mathematics, i.e. the formula that we need, or the definition we need for the heat of formation, it is the heat change that takes place when 1 mole of any substance or compound is formed from its elements. So in this case, unfortunately, we are not making 1 mole. So from the point of view of the heat of formation, we would not use that. So let's take a look at the bottom one. A half an N2 plus 1.5 H2 gives 1 mole of NH3. Say it again. A half a mole of nitrogen plus 1.5 moles of hydrogen will give 1 mole of ammonia. What's the definition? It is the heat change that takes place when 1 mole of a substance is formed from its elements. Now, the bottom equation fits the bill perfectly according to the definition. However, this is bad chemistry. It's bad chemistry, but it is very good mathematics. Okay, it's good mathematically. Here, this is good chemistry. But as far as we're concerned for our definition, it's bad maths. Now, because we're moving into the mathematical side of this, it's the good maths that we're more interested in. Okay, why is this bad chemistry? It's bad chemistry because nitrogen exists as a triple bond between 2 N atoms. Okay, that's N2, and that's the way nitrogen exists in the atmosphere. That's the way nitrogen exists elementally. So when I'm talking about a half an N2, I'm talking about this. That's not nitrogen anymore. All right, so that cannot exist on its own. So why it's bad chemistry is that doesn't exist. 1.5 H2s doesn't exist, but 1 mole of ammonia does. So then why do I favour this? And the answer is because what we're about to go into is a mathematical exercise. Okay, so in this case, fractions will be perfectly acceptable and allowed. So we have to kind of deviate from the fact that the fundamental principle of chemistry says all reactions occur according to simple whole number ratios. We're now going into a situation where, mathematically speaking, with Hess's law, we may use half molecules or 1.5 molecules or whatever we need mathematically to get us through the procedure for Hess's law. Okay, so which one should be used? Well, the bottom one. Why? Because it's the only one that makes 1 mole from the elements. All right, so keep that in mind. Now, here's Hess's law, and this is a definition again that you have to remember. Hess basically said the following. If you have a reaction, A plus B going to C, okay? What Hess said is the following. The energy change for this particular reaction only depends on where we start and where we finish, and doesn't care about the pathway. So in other words, what does that arrow stand for? Well, we don't care. In Hess's law, it doesn't matter. Hess says that the heat change for a given chemical reaction only depends on the initial and the final states and is completely independent of the pathway followed. Now, why is that the case? Because look, you could have A plus B going directly to C, but you may have A plus B going to D first before it goes to E, before it goes off to F, then it goes back to G, then it might go to H before it gets to C. Who cares? Hess's law says it's only dependent on where we start, it's only dependent on where we finish, and we don't care how it gets there. Okay, so that's your definition. Hess's law states that the heat change for a given reaction is dependent only upon the initial and final states and is completely independent of the pathway followed. Please remember that definition and learn that definition. Okay, so now there are 5 definitions completely. Heat of reaction, heat of combustion, heat of neutralization, heat of formation, and Hess's law. You have to know those 5. But there's no more you'll be glad to know. That's it. There are 5 definitions for this. I would say take a piece of paper now, write down those headings. Heat of reaction, heat of combustion, heat of neutralization, heat of formation, Hess's law. And then write down the definitions beside them and learn them off. Okay. Now, Hess's law, as we said already, the heat change for a given reaction was dependent only on the initial and final states and is independent of the pathway followed. Please learn it. That is Hess's law. Okay. This gives us a mathematical way to calculate the heat of reaction for the reactions that are difficult to carry out in the lab. Now, not all chemical reactions are very simple to carry out. Some chemical reactions are tricky. So what we do instead is we say, okay, what do we start with? Well, in the case of thermochemistry, we begin with the elements of the substance we want to build. What's our final state? What's the compound I want to end up with? So we write that down. And then we want to see, by using reference to any of other relevant reactions, how we can use the information there to build the expected energy change for the reaction that we find difficult to carry out in a lab. Okay? So, since only the initial and final states of the system are needed, existing chemical reactions and their known heat changes can be reversed, added, subtracted, multiplied, divided to build up the reaction whose heat change we want to calculate. Okay, so listen to that again. Some chemical reactions are difficult to do in the lab, so we don't do them. If we want to predict what energy change would take place in a difficult chemical reaction, we go back and we refer to existing reactions and their existing known heats. And we bring them together, relevant reactions, in order to use their bits. Again, it's like Lego. You're going to use the bits in the existing equation to build the equation that you require, and the existing heats then will be mathematically used to determine the heat of reaction for the difficult reaction. Okay, now sounds difficult in theory, but in practice actually it's quite easy. So questions using Hess's law must be approached in a systematic way. So this is why I call this a set piece. There is no other way to answer Hess's law except to follow the rules. Okay, and number one is write out the equation that you want to calculate the heat for. Number two, write down the existing information that is given to you in the question. Number three, make sure that the positions of all the particular reactants and products are in the correct place. Number four, check the quantities of the reactants and the products and make sure that they're correct. And number five, eliminate what is not required in my final equation. And then what you should have left is enough information from the existing pieces of chemical equations that are there to build your new equation. Okay, so number one, write down the equation you require and underline it. Number two, write out the other equations using the data that you're given. So the lovely thing about this is they'll give you the building blocks. They'll give you the Lego set and they'll say, go away and build this equation here. Okay. Number three, align the substances according to equation one. Number four, make sure that the quantities are correct. And number five, eliminate. So a 5-step procedure. Write down, number one, the equation that you want to get. Number two, use the information given and write out the equations of what's given to you. Number three, align the products and the reactants into the correct manner following what you wish to build. Number four, multiply or divide the quantities to make sure they match what you require. And lastly, then eliminate what you do not require and gather the result. So here's an example. The combustion of one of the C4H isomers is described in the following balanced equation. 1 mole of C4H8. Now C4H8, just think about that for a moment. C4H8, 4 carbons, MEPB, but there's only double the amount of hydrogen. So this is an alkene. So this could be butene or butene. We're not too sure. It doesn't say. It says one of the isomers. Plus 6 moles of oxygen will give 4 moles of carbon dioxide and 4 moles of water with a heat change of minus 2,710 kilojoules per mole. Now listen to the next part. The standard heats of formation of water, carbon dioxide, are minus 286 and minus 394 respectively. Calculate the heat of formation, here it is again, of this C4H8 isomer. Now, question number one, what do I want to calculate? The answer, I want to calculate the heat of formation of C4H8. Now, here's the reason why you've got to learn the definition. The heat of formation of C4H8 is the energy change that takes place when 1 mole of C4H8 is formed from its elements. Now, what are the elements involved in C4H8? Well, carbon and hydrogen. And don't forget, hydrogen is a diatomic gas, so it's written down as H2. Now, balance this thing. There are 4 carbons on the right hand side, so there must be 4 carbons here. There are 8 hydrogens on the right hand side, so there must be 8 carbons here. Okay, and we want to calculate the heat of formation. So delta H equals what? And that is what I have to build. Now, if that's my required equation, where are my Lego pieces? Well, the answer is there's 1, there's 2, and there's 3. There are 3 statements which have been made in this question that we have to turn into chemical reactions. The first one, C4H8, is given to me, so I'm going to write that down. It's up on top. With 6O2, goes over to give 4CO2 and 4H2O. And I know that the energy change for that reaction is minus 2710. Now, where are the other 2 equations? Well, they're here in this sentence. The heat of formation of water. What does that mean? It's the energy change that takes place when 1 mole of water is formed from its elements. And don't forget, water is formed from hydrogen and oxygen, which are both diatomic molecules. So I have to make sure now that I don't touch the right hand side. I'm only allowed 1 mole, that's the definition. So 1 mole of H2O is formed from its elements. So in order to manage anything, H2s are balanced, but I have to put a half there. And because this is a mathematical exercise, that's okay. The half is fine. Next one, heat of formation of water is minus 286. And the third one, the heat of formation of carbon dioxide. It is the heat change that takes place when 1 mole of carbon dioxide is formed from its elements. Now, carbon dioxide is formed from carbon and from oxygen. So therefore, you write down the elements in their elemental form. Carbon is C, oxygen is O2, and there's no need to balance anything. And delta H for that reaction is minus 394. Now, here's what I need to do. I need to use those 3 building blocks, Lego pieces, in order to build this equation here. Okay, so you've done step number 1. Step number 1, write down the equation you require. Step number 2, write out the equations of the heats that are given to you. Step number 3, manipulate the pieces so that they fall into the correct place. You want to align them. Now let's just check. I want, in my equation, I want C4H8 on the right hand side. But in my Lego set, my C4H8 is on the wrong side. So here's what I'm going to do. I'm going to reverse the order of that equation in order to put the C4H8 on the other side. So let me just write down there, reverse. Okay, so I'm going to reverse this, which means that you write it out backwards. So you write out, let me just do that for you quickly. So I'm going to erase the 4H2O and the CO2 and the 6H2O and that one there, and I'm going to reverse it. Okay, now just keep this, watch this carefully. Pen. What was that? The top one. So that becomes 4 CO2 and 4 H2O goes over to give C4 H8 and 6O2. Now, I have reversed the equation. So also then I have reversed the flow of energy. If the forward reaction gives out heat, the backward reaction is going to take it in. So you change that symbol to plus. Okay, that's a 2 by the way there. Okay, so now do I have my C4H8 in the right place? Yes. Is my carbon and required hydrogen, required carbon, required hydrogen, are they both on the left hand side of all their equations? Yes, there's carbon and there's hydrogen. So I have aligned the building blocks into the correct position. Step number 4, make sure that the quantities are correct. Now, what I want to build, this is the equation I want to build, okay? So I want to build this. Now take a look. I want 4 carbons. I have to have 4 carbons. I've only got 1. So what I'm going to do here is I'm going to multiply the entire equation by 4, which will give me 4 of them, 4 of them, 4 of them, and also keep going right to the end. You multiply the energy by 4 as well. So 394, when multiplied by 4, becomes 1576. So let's change that. 1576. Now you'll notice I haven't reversed the equation, so the sign stays negative, okay? And lastly then, I want 4 hydrogens. And up here in the second line, in my Lego set, I only have 1 hydrogen. So I have to multiply this line by 4 as well, which will give me 4 of them. Now be careful, 4 halves is 2. So let's get rid of that half there. So 4 halves becomes 2. So you put a 2 in front of that, a 4 in front of that, and the 286 gets multiplied by 4. 286 gets multiplied by 4, and that comes out as 1144. So 1144. 1144. Okay, so now I'm on step number 4 at this stage. Only 1 step left to go. So what have I done? I have built the equation I require. That's in the box at the top here, this one. I have then taken the 3 equations, which are my Lego playset. These are all the bits and pieces that I want to build this. I have made sure that in accordance with the equation I require, the various different parts are in the correct place by reversing equation 1, swapping it round and changing the sign in front of the heat. I have then made sure that the correct quantities of each of the substances I require are in my Lego set. And finally, I'm now going to get rid of those things that I do not require. Now watch this, because this is a lovely thing about this set piece. It'll let you know that you're correct. Let me just see pen. I'm going to just do this in blue. Okay, so let's see what we don't want. Is there room for carbon dioxide in my final answer? And the answer is no. So therefore, on the left-hand side, there are 4 carbon dioxides. But on the right-hand side, there are 4 carbon dioxides. So because the same quantity is on both sides, they cancel. Good. Okay. Is there room for water in my final equation? No. So the 4H2O on the left-hand side will cancel with 4H2O on the right-hand side. And then we don't want any oxygen. So the 6 oxygens on the right-hand side will cancel with 2 and 4, which is 6. And at that stage, everything that you require should be what's left. So let's go down and see what's left now on the left-hand side. The only things that are left are 4 C's and 4 H2s. Okay, what's the only thing left over here? C4H8. Does that match what I wanted to build? The answer is yes. So in order for me to get delta H, all I've got to do now is stick these numbers into the calculator. So 2710 minus 1144 minus 1576, and that comes out as minus 10 kilojoules per mole. And that is the answer to the question. So there's a set piece involved in all of this. Okay, and I've gone through it with you. I'm also going to go through it here by means of typing, just in case. Watch. So what's required? This equation here is required. Calculate the heat of formation of C4H8. So I want to make 1 mole of that stuff from its elements. So I require the heat of formation of C4H8. Okay. What other information is given? Well, the heat of combustion of C4H8 is up there. That's that one. That's given to me. So there's one piece of information. Then we also have the heat of formation of water and the heat of formation of carbon dioxide. They're also given. So there's my Lego set. There's the things I'm going to play around with to try and build what is required. Okay. And then write the chemical equations to represent all the given data. So let's do that. Heat of formation of C4H8. It's 1 mole of C4H8 formed from its elements. That's the definition. So there it is. And that's what we want to calculate the heat change for. Okay. What is the heat of combustion of C4H8? It's minus 2170. It's given to me up there. I'm just going to reproduce that down here. Then we have the heat of formation of water, minus 286. It's the heat change that takes place when 1 mole of water is formed from its elements. And then finally, the heat of formation of carbon dioxide, 1 mole of carbon dioxide formed from its elements, and you get that. Okay, so I want to make that from these. That's the whole idea. So how do I do that? Well, run them down. Okay. Did we do that already? C4. Oh, we didn't. Okay, we do that in a second. All right, so that's what we do. In terms of this thing, we write these out, as I went through a few minutes ago. We write out C4. Is that the one there? Let me just check. It is. Yeah, we're going to do it here. So C4H8, there it is. That's what we want to calculate. Heat formation. Now, there's the Lego set. There's the building blocks. And I want to check the positions. So just watch this very carefully. That's what I require. That's what I want to build. So all these pieces in here are going to be used to build up this equation. But they must be, first of all, in the correct position. So C4H8 must be on the right of the arrow, but it's not. So what am I going to do? I'm going to reverse equation 1. Watch carefully. Bang, done. Did you notice that the energy sign changed? Because it's the backward reaction. We're reversing the flow as well. Equations 2 and 3 must be multiplied by 4. Why? Because I want 4 carbons and I want 4 H2s. So both of those get multiplied by 4, and also the energies are multiplied by 4. Now, if we've done that correctly, everything we do not require should cancel. CO2 with CO2, 4H2O with 4H2O, 6O2 with the 4 and the 2 that's there, leaving you with the bits that are left. You bring them down into an equation at the bottom, you take the heats, put them into your calculator. Whoops, 550. How the hell is that? Check that again. 2170 minus 1144 minus 1576. Oh, mustn't have done it right the first time. Anyway, minus 550 in that case. So you put these in. All right. 2170 minus 1144 minus 1576. Oh, minus 550. Okay, well, there's your answer. Minus 550 kilojoules per mole. I got minus 10 when I did. I must have written down a number wrong or something. Okay, that's it. That's how it operates. Okay. Now, I'm going to leave you with those slides. I'm also going to put up a few questions in relation to this, but I'm going to go through another work example in a second video. That's just to finish off the slides that are there. You can go through them to your heart's content. Make sure you understand that example. I'm going to give you a video lecture or a video on how to do a question from the exams. and then I'm going to throw some at you and ask you to try them yourselves. But please remember, these will be in your summer exam. It's vital that you understand how these work and how they're calculated.